I've put together a little bits that we have covered already for this particular lesson. It's not on momentum, the last topic we just covered. It is going to be on our forces, and we're going to introduce using a Newton meter. Have you used a Newton meter before? So on this you will be able to, you'll have a reading, it's in grams. On the other side you have got our newtons. So it's converting gravity, force of gravity, with the mass, and doing the calculation for you basically. So to work out what the force is. So we can measure now physically what sort of force it is when we look at pulling these trolleys and a piece of wood across different surfaces. We can measure how much force it takes by just looking at the reading that it has. Okay. So we're going to be adding some slotted masses. Remember mass and weight? Masses is just the amount of matter that's in it, and these are going to be in grams, not kilograms. And we are going to attach this, and then you're going to do some readings. They're 50 grams each, and I'm going to get you to write in this table. You're going to look at the increases in the weight as we add more masses to it. About 50 grams at a time. And then we'll look at measuring some other objects, like pencil case, and see how much, see what the mass is, and we can look at the weight as well. Okay, just by reading it straight off in Newton meter. Okay, so I'll get you to write this down first, please. This half. We'll get this done first, and then the second half we'll do through this one. Yeah, just a simple diagram would be fine. To take these slotted masses off, you've got to lift them off and pull them out. So you've done 50 grams each, and you're going to take all 9 of them off. Don't lose them, don't drop them, please. Too much noise. And just check the bottom, make sure, because this unscrews, just make sure that it's tight. Okay? Otherwise it was loose and you can just drop off. Right, so you're going to take your Newton meter, and so with the grams firstly, so you're going to put your hook on, and you're going to see, then record what measurement it is to the best you can. Okay, if this is 50 grams, it should be showing 50 in there. Does it show 50? So it's quite accurate, right? Yep. So that's your first one, is 50 grams. So then you turn it around and have a look at the newtons. And how many newtons is it? Bounce it like that, and it's going to change it. Okay? With my energy. Right, so it is supposed to be. Right? And then you're going to go through and close it. And add them together. So somebody you might want. So without bouncing it, it's really hard to keep still. So how many grams?
100, it's like not even 100, it's like less than 100, it's like 9 pounds.
Okay, we're going to say it's 100. Okay. It should be, because we know that this is 100 grams. Yep. And so how many newtons should it?
Oh wait, it's 1.
1. Because remember, how how many, if it's a kilogram, how many newtons of force is acting on 1 kilogram?
10.
10, yeah. Okay, so that's why, because we've only got 500 grams here, we haven't got to a kg, and then it goes to 5 newtons. Then if we add another 500, that's 1 kg, there's 10 newtons. Okay, right, so you're going to be adding them. Do you want to read this? You want to put these on? So you're reading your grams on this side, and newtons on this side. Okay. So we take those off. Oh, okay. Yeah, I'll hold on to that. You. It's going to be pretty consistent. It should be.
Something like that.
This is not that accurate, is it? It should be 1.5. Yeah. Okay, so what I can see 100 grams on this side. How many newtons of weight? 1. Okay. So it's going to be 1. Yep. So put the next one on. Yep, 202 newtons. This Newton meter is more accurate than this one. Yeah, I'm wondering if I can adjust it. How's it looking now?
Yeah.
So it's 400. Now it's better, eh?
Yeah.
So 400. So you got 400 grams. 450. Just wondering if I can just adjust this. Just a bit. No, I won't. Let's see. Wait. Because what will happen, the extension of the spring will be too much. Go past its limit. Okay, what do we got now? 100. It should be.
3.5 Newton.
Yeah, 3.5.
What's wrong with that class now?
What is it measured in?
Grams.
It's measured in grams, yeah. You can see that. It's called mass, yeah. And what is that? That's what? It's the amount of matter, okay? Mass, amount of matter, right? I am 76 kgs. That is the amount of matter. It's my mass, it's not my weight. When I hop on those scales, it tells me in kilograms. But scales, remember they go, oh, what's your weight? Oh, let's hop on the scales. And it's not, it's the amount of mass. That's why we've got to keep reinforcing that. So, weight, then, Emma, what is weight? Yeah. What's the difference though? We know what mass is, matter. What is weight?
Amounts of the Newton.
Yeah, it's measured in newtons. Yeah. So there's a force acting on it. What is that force?
Of gravity.
Yeah, gravity. Okay. So it's all about weight. It's all about gravity. And how many newtons per kg?
10.
What's that magic number? 10. Okay. Yeah. So all this is doing. I'm not filling in all of this because it goes up. It corresponds together and is correlated. So this weight is about the gravitational pull. And so we've got 500 grams. It's 5 newtons. If we added another 500 grams, here's 1 kg, 10 newtons of weight. All right. Okay, so measure a couple of other things, like your pencil case, and let's see what the mass is and the weight. Let's see what the mass is and what the weight is. So we've got some pencil cases here, and I have there and there. All I need is a little hook on there, which is good. And so you can do yours as well. Let's see what they are. So get your Newton meter. As long as it's not over 500
Maybe it is. Who
Think
knows?
so?
You want to know? Let's see. Long.
Okay, that's more. We don't want that. Shouldn't be more than 500 grams. Yours won't be.
Yeah, hers will be.
Oh, it looks like it is exactly 500 grams. Okay, so if it's 500 grams, how many newtons?
5.
Okay, good. And what have we got here? How many?
1.5. 1.4.
Okay, 1.5. Yeah, because it looks like 150 grams. Yeah.
Okay.
Yeah. All right. Okay. Matilda, empty out your bag. Have a guess. Have a guess. Okay. Yeah, I want you just to make a guess, a prediction is what it is.
So I'm at 100.
So 200, what do you think?
150.
150?
200.
No, I haven't checked. It's 500.
About like 100 or like
Oh.
200?
Yeah, it's hard to, I reckon about 230 grams. What do you think?
300.
300? Okay, we've got a range. Okay, let's have a look. Let's see what it is.
Wow. 400.
Oh, okay, so the closest was candy. Yeah. I know, it's, okay, very good. All I'll do is, it's really hard to judge.
Let's say, can we try this everything out?
Oh, so now you, how many points have you got?
A lot.
That is a lot. Okay, so we're going to do a guesstimate on this one as well, of an empty.
Okay. 200.
Well, let's have a look. It's quite hard to guess, isn't it?
100.
Oh, okay. Maybe maybe 100.
Okay, so you reckon 100?
Yeah.
Yeah, it's quite light, hey?
It's 130.
130, yeah, okay, so that was a good guess.
That's right.
130. Yep. Okay, so the reason I just wanted to try that is just guesstimating, trying to work it out. And it's very hard to accurately work it out unless you've got some form of measurement to work with. Okay, second part. I would like you to write down this number 2 and 3, please. And I'll give you about 4 minutes. You're going to have to write pretty quickly because we've got a little experiment to do with this. And this is just a calculation. And math. So I'm increasing the amount of friction, which will then expel the trolleys away from each other. But these trolleys, they've reduced the amount of friction. We've obviously got bearings in here, the wheels. So it can float along really quickly. I want to increase the friction. And that's why this block is easier, okay, than this trolley. So what you're going to do now is, so we've got this block of wood. It's on a flat surface, stainless steel. There's not a lot of friction. There is some, but we need to know, okay, how much force it's going to take to move this particular object. Okay, and so what you remember from static is you're moving the object from stop. Once you get it moving, you're then going to have a look at the dynamic force, because it'll reduce, because you've already got that momentum moving. So if you come up here, and you're going to have to be a little bit, you're going to have to do it a couple of times. So what I'm going to get you to do is to look, and one of you's going to be reading it, because you're going to have to, you can't stop, you're going to have to keep going with it. So I am looking at it, I'm starting to get it going, it's about 1 Newton, but I'm going to get to work with that, and I'm continuously moving that, 1 Newton of force, 1 Newton of force, just over 1 Newton of force as I'm moving it along. Okay, I want you to try it and just double check that I've got it right. Okay. To move this particular object. Okay, so up you come and let's give it a pull and you do a reading off it. I hate to do it from down here, down the end, and then just randomly pulling it like that. So it might go sideways. Can you see the reading? Can you see the reading? So 1.5. I can see it from this side, so others might have to come from this side.
Yeah, it's 1.
Yeah, that one. Sometimes it depends. You can increase the force, okay, because we're just making it steady. If you wanted to go faster, what are you going to have to apply? More energy, more force. Yeah. Okay, so you're good to go to tilde. Sure that's on there. The reading's over here now, so we'll try and. So if we have it like that, you can do your reading there. Come on, you're right.
Yeah.
This is worth video. I told you to trip on over that. Look at that one. It's quite hard to read out because it's continuous to move it. Just move it steadily. So just go like that. Okay, so we're going at the same speed. What is it reading?
1.5.
That one, it is 1.58, and now it's starting to go sideways. Yeah. Okay, so about 1.5. Okay, so I'd like you to write that in, please, on the bench. So you've got the force is 1.5 newtons. Move along. So you're going to have to be, yep, now you're going to do the same. And I want you to, so from there. Yeah, so someone's going to put along, you have to be quite quick with it because it's quite short. Okay, so someone pull that along. Now remember it's static at the moment. So now, well, 2. Okay, then, yeah, so give it another go, let's see if that is correct. Oh, was that 2?
1.5.
Yeah, 1.5. That was what I give it another go.
Fast or slow?
Well, you try and do it fast, and what are you going to do? See here, so over 2, but why? So you were applying more force, but what was happening to the object?
Slower. It was not going faster.
When you applied more force, that was going faster.
But when I start doing it, it's not going.
Okay. Yeah. Okay. So it takes more force because it's static. It's going to take more force initially to get it moving. Once it's moving, it doesn't take as much force. It reduces. Okay. So give it another go. And try and do it a little bit faster. Let's see. Or like you did before. So it's still about 2, eh?
Yeah.
About 2 newtons. Okay. Why is it taking more force? We have not changed anything, any variable. We have not increased the mass or anything.
The mat.
The mat. Okay. Why?
It's not as smooth as the stainless steel.
Yep. So we're increasing the what? Friction. Yeah. Increasing the friction force. Okay. So friction is a force. We have to overcome it by producing a greater thrust. This is our thrust. You know, when we were talking about the arrows and okay. Right, so up on here we're writing how many newtons on the board? Okay. 2. 1.5 newtons and that was 2 newtons. Okay. So, and which force, which takes more force and why? So it was the mat. So we needed to overcome friction force. The friction force. And friction, was there any change Really? Was there a greater amount of force when it was on its own? You know, when it was to get it moving? There normally is more, but it hasn't got enough mass. If we had a greater mass, it would be more noticeable. Okay? So for the static friction, so we're saying it was 1.5, and then the dynamic, once it was moving, it's about 1.7. This is for bench. So about 1.3. Relationship, acceleration, mass, and forces. So, very heavy at all. Okay, so then I've got this bottle. I'd like to have some bigger slotted masses, you know, like bodybuilders' weights, put on there, but we haven't got any. So, come and measure this and see what the mass is, please. Come and measure this. Tell me what the mass is in kgs. Okay, we probably need 0. Yep. So 0. You don't pen there?
Nope.
Okay, this is a cheapie I bought from Plaza Mall.
Oh, there
There you go. Nice. Okay. Trolley and the distilled water. Okay, put this on top as well. Oops. Right.
1. Wait, no, it's
Keep moving.
Okay, how many kgs? This has got pounds because it's American in black. So blue is in kgs. How many is it?
Blue is in kg.
5.
Yeah.
5 or 4. It's about 4.
Yeah, it's about 4. I'm going to round it up to 4. So it's going to be easy to calculate. Okay. No, we'll stick with 4. Yep. Okay, so 4 kgs. Can you go and write that down? The mass of the trolley and water is 4 kgs. Okay. You have a hook. Yeah. This is trolley. Now, we know that it's 4 kgs, and that's the mass. We are going to apply a certain amount of force to it to get it accelerating, but it's probably better if we do it on the ground down here, because we've got it further along. Okay, because by the time we get it going, it's going to hit here and just fall over. Alright, so somebody is going to pull this along. Somebody. Candy, is it your turn? Okay, so you are going to pull it. You're going to have to stand like this because you're going to have to get it going and pulling along like this. So once it gets going, I want to know what the force is. You girls need to look and see what the force is to get that trolley going. Because once it's going, the momentum is going to keep it going. We need to know what force to get it accelerating, all right? So, Candy, you can go. And girls, are you watching?
Yeah.
Okay, what's the reading?
Morning.
It's quite hard, isn't it, to calculate from there? Okay, ready? Hang on, let's have it from stop.
I can't see the kg.
No, you don't want kgs, you want
I can't see the
newtons.
Newton too.
Yeah. Okay, we want to accelerate it, we don't want a steady flow. So let's bring it back here. Right, Candy, you might have to do it. As soon as you pull it, tell me what measurement it goes to, how much force you have got it going. Give it a good yank. Right, could you see what it was?
0.5 Newton.
0.5?
Maybe 0.4.
So I'm going to increase because I want to get the acceleration going, so I'm going to give it a good pull. Okay, so and I'm going to let it go, so can you stop it? Ready? Okay. That was 5 newtons of force. Okay, I gave it a good pull. Okay, 5 newtons of force. how much
4.
mass?
4.
4? Okay, let's do a calculation on that particular one. How do we know what the acceleration was? The force was 5 newtons. What's the acceleration? What's the formula for acceleration?
Divide.
Yeah, you're going to divide it. So remember, force equals mass times acceleration. We're trying to find acceleration. So acceleration is going to equal...
Force divided by mass.
Yep. So what is that? Force is 5.
1.25.
Yeah. Divided by 4, which equals
1.25.
1.25 watt. We're doing acceleration. What are the units?
Newton.
Meters per
Wait.
second per second.
Good. Meters per second per
Wait,
second.
never mind. I didn't hear
Yeah. Meters per second per second. It's a 1.25.